Okay, so yeah, thanks to the organizer for inviting me again, despite my previous talks on the topic. So, well, this, as some of you already know, is part of a longer-term project aimed at studying mathematical structures that occur while trying to understand the structure of syntax in natural language. So this is based on this paper, which is in the current conference volume. And the more general question that it fits in is, okay, there's a how is language sitting in our brain in a way? And this general question can be broken down into some more specific questions. How it is acquired, learned, how languages change over time. What I mean by language, of course, is I'm mostly interested in looking at the large-scale structure of language, which is the way syntax is organized. And for that, I take on a point of view which is very familiar in linguistics, which is to try to parameterize syntax as a kind of a sequence of binary variables associated to a given language, where a binary variable is a yes/no answer that basically tells you whether a certain kind of syntactic construction is allowed in that language or not. And so, linguists have been collecting data about this type of binary variables, this type of syntactic parameters for a fairly large quantity of world languages. But there is so in a sense, this point of view is appealing for a mathematician because it's like a set of coordinates on the space of language. But I mean, there's some kind of, so that what I mean as just make us like a standard example of what these parameters are like. So certain languages, for example, are had initial, and certain languages are had final. So that's like a yes/no type of thing. And some languages, other examples, in some languages you can drop the subject of a sentence and the sentence is still grammatical. In others you cannot do that. So there's a series of rules like that either work one way or another. And as you can imagine by these examples, you can immediately realize that there are lots of rules like that in the syntactic structure of a language. So you expect to have like a long list of these binary variables of the order of some hundreds at least. And so one of the main problems is like what is exactly that you are classifying? And so the problems that linguists have is that there's no complete classification of all the possible syntactic parameters. And also, there's no good understanding of what are the relations between these variables. So what is an actual set of independent coordinates on this? So you would like to be able to extract only those variables that are really independent and somehow drop the information, irrelevant information that comes from variables that are determined by other variables. And also, I mean, one knows that these parameters have been evolving in time as languages change, so there's some dynamics going on that one would like to be able to model. Over all of these problems, there's the fact that collecting this data is difficult. So there are available databases, but they are very incomplete for certain families of languages, much more complete for others. So one has to necessarily work with whatever data are available. So the data mostly come from, as I said, various databases that are currently, I mean, they are kind of being improved by work of linguists, but it's a sort of work in progress to get these classifications for more and more languages. So what I'm going to focus on is two aspects. So what I'm talking about here is ways of trying to identify relations between some of these parameters, identify them in a computational way from the data. So there's one aspect that's also interesting and that will play a role in the model the computational model that I'm going to show in a moment, is that if you look at some of these parameters, they are very unequally distributed among the world languages. For example, there's certain parameters that describe the word order of subject, verb, and object. And there are languages, of all the possible combinations, there are languages that have that combination expressed. I mean, where that combination is grammatical in that language. However, the number of languages that have some of this combination expressed is very different. There are basically two combinations that almost occupy the entire landscape of world languages. And all the other combinations are extremely rare. And this also happens with other parameters. So they're very unequally distributed among the world languages. There's been some speculation or some hypothesis or proposals that this unequal distribution of parameters across world languages reflects some kind of neuroscience aspects of the way these functions of this syntax calculator is actually stored in the brain. And however, this is controversial. I mean, there are other, for example, historically, some of these parameters have tended to move towards one of those most frequent configurations. And there are proposals that there's some kind of intrinsic reason why that should happen. So linguistical intrinsic reason as opposed to neuroscience reasons. So the point of view that I'm going to take on this is based on modeling, computationally modeling these data into a sparse distributed memory. So Canerva networks or sparse distributed memories were introduced as a kind of a computational model of associative memory, of human memory. And they were built in a very simple way. So you have some large space, some large ambient vector space, or binary vector space over the field of 2 elements. And inside this large cube, binary cube, you pick samples of what is called hard locations in the construction of the Canerva network. And you look at around each of these locations, you look at the Hamming sphere. And you look at the Hamming sphere that has radius that's just slightly larger than the median distance, so that there's some overlap between the Hamming spheres. And so what you do is when you store something into the network, you write your data at the hard locations in this, so you store a certain datum, you look at the address of that binary datum in your big space, and you look at all the hard locations that are within its access sphere, and you write at all of those. And when you read at a certain location, you look at all the accessible locations from there, and you take an average of what you read there using a majority rule because it's binary data. So the interesting fact is that the interesting fact is that one thing that Canerva networks are good for is that they are good at reconstructing corrupted data. So and in this way they detect dependencies in your data set, in the sense that if some of the data are slightly corrupted but they are very well reconstructed from the rest, then it's a sign that there are dependencies in that data from the rest. So you can kind of assign a coefficient that tells you how well reconstructible a part of the data is from the rest. And that's a way of kind of having an estimate of which of your variables are the most independent ones and which are more likely to be dependent. So the idea, in a sense, is that the idea why this is a model of memory is the idea that most items that are stored are unrelated, but most pairs are linked by a few interactions going around these accessibility spheres. And the idea of associative memory is that whenever something falls into two different access spheres, it's a kind of associations between two different stored items in memory. And so when you write data at a certain location, as I said, you write it at all the points in the access sphere of that location, and when you read, you make an average of that. So in a sense, this has been posed as a better model with respect to the usual kind of separating hyperplanes, like perceptron kind interpretation, as a better model of the way that information is stored in the human memory. So in a sense, that's why the choice of using this kind of model, because we store, when we learn a language, we store the information about the syntactic parameters of this memory in our brain in some form, and sort of taking this idea that really we could think of it as being stored in a Canerva network way. So the way we use this to analyze the data is to pick a certain number of languages, about 165 languages, and 21 syntactic parameters, which were chosen so that they would be very well mapped for all of these languages. The languages are chosen so that they are spread across several different language families, so they don't all belong to like the Indo-European language family or something like that, so that one has a picture that's sort of not dependent on a specific language family. And also the parameters are chosen so that it's known that there are relations between them, although these relations are not explicitly, the explicit form of these relations is not known. And then looked at what happens if you corrupt a single one of these parameters at a time in this data, and you look at the recoverability from the rest of the Canerva network. And you can assign a coefficient of recoverability, which is based on an average Hamming distance. So the lowest score means the most easily recoverable ones, and the highest score means the other. So the parameters chosen are exactly this type of word order parameters that I described before. And the fact that those are so unevenly distributed, so these are the frequencies among this data set, not necessarily among the whole world languages, but among the 165 that we looked at. The fact that they're all so differently distributed actually plays a role in the way the Canerva network behaves. So there is an overall effect. So there are two effects. This is what one finds. So this is how these different syntactic parameters behave with respect to recoverability in a Canerva network. So these are the highest, the most recoverable are down here, and the least recoverable, so the most independent variables are up there. So one can see that there are two kinds of effects. So there's an overall effect that depends only on the different distribution of parameters across languages, on the frequencies of expression. And you can see that by running the same with random data with the same frequencies. And something got lost. Okay. Some pages missing from here. I don't know why. Well, so there's an overall effect which for some reason doesn't show on the screen, which is basically a curve that that's much sharper than this one, that only depends on the frequency of expression. And if you normalize with the curve, you see that there's an effect which does not depend on the frequency. And so the effect that does not depend on the frequency is the one that depends on the existence of relations between these syntactic parameters. And the other overall effect is the one that reflects the different distribution frequencies. So when you normalize with respect to prevalence, with respect to the frequency of distribution, you find these are examples of parameters that are most independent or least independent among this set. So what one would one like to do based on this? So first of all, it's one could look at what happens. So as I said, we picked the data intentionally so that they would cut across all different language families. For other kind of analysis of data of syntactic parameters and geometric structures on syntactic parameters that I did before, and so that there are interesting phenomena that are specifically dependent on language families. So another thing that one can do is actually break down this type of Canerva network analysis by language family and see whether the effects are different. Also, there's a so one would like to extract some better understanding of these additional effects that don't depend on frequency, which are, what do they actually mean in terms of relations. And moreover, as I said, Canerva networks, we're using them because they're possible models for human memory, and so can one use this to actually construct some model of how syntax is stored in the brain. Okay, so I think I've probably taken a little more of the time that I had. So
no, it's okay. Okay. Because in fact, we have more time due to the cancellation of one talk. Okay. No problem.
Okay.
So now we have time for questions. Can you ask you about, because you present a new general method of statistics in some sense to analyze. And do you think that every kind of data could be analyzed for the variability, inter-subject variability? Because it's something I heard now by several people working in neuroscience, especially, that we were very interested by rules, by mean and variance, but probably it was not sufficiently explored the structure of inter-subject variability to understand the process. So my question is, do you try to apply this kind of analysis to other kinds of subjects than language?
Yes, so that's possibly yes. I mean, you can use this just as a model for trying to analyze dependencies between data sets. Right? Okay, so in that sense, it could be applied to any other kind of binary data set that you want to, where you want to search for dependencies. In this case, you look for this recoverability factor when you corrupt only part of the data, and you use that as a way to see how much it's dependent from the rest. In the sense of language, the point is that we're also hoping that these Canerva network model, thinking of them as possible models of human memory, they might
That's difficult to see the link
connect
between because you say you have a model for memory, for animal memory, something like that, and now you apply to something totally different because you speak of the whole humanity.
Yeah, but see, for example, because there are these proposals that one would like to relate the prevalence, I mean, the frequency of expression of these parameters across world languages to some neuroscience data. So in a sense, they would like to say that certain configuration of these parameters are more prevalent because of certain ways that the Broca area of the brain is structured. And so these proposals are at the moment, I think, really conjectural. But here, in a sense, you see that the prevalence, the frequency of distribution is built into how the recoverability in a Canerva network works as part of the effect.
In what sense?
So if we imagine that this is how these parameters get stored in the brain, it might provide a different kind of support for the idea that there is a correlation between the frequency of expression across languages and the way that these parameters are stored in the brain. At this level, this is just a proposal, but we're trying to find a different way to look at it.
So this may be related what you just said, but I think a first step would be within a Canerva network to understand how structurally a young child learns a language, step by step.
Yes.
Not in detail, of course, but how structurally. Has that been done already, or is that
Yes, that's right.
work in
I mean,
progress?
as I mentioned at the beginning, one would really like to link this to models of language acquisition, because the way that language is stored in the brain depends on the way that it's acquired. So indeed, that's a very crucial question. Yes. Yeah, there are some dynamical system models of language acquisition, just based on some kind of Markov processes that could converge to a given grammar. And I think one can try to couple that to this type of network model. That's definitely part of the thing.
Just a question about the sparseness. You said that you need the parameters to be sparse, the memory to be sparse, and so maybe there is a trade-off with the recoverability. If you change the sparseness of if you increase the parameters, for instance, you should decrease, the recoverability somehow. And so I was wondering if there is such a trade-off in between the two.
Between
the sparseness of the sparseness and the recoverability.
Yeah, there is in addition to this overall effect that depends on the frequencies, there are variations, fairly visible variations from that effect, and so I think those really are kind of dependence relations between some of these parameters, which are not just expressed through the prevalence relation. So there's something.
Yes,
there's something more that really needs to be analyzed in terms of actual dependence relations.
And I was wondering, for instance, this sparseness. Do you think, as you were mentioning, as a model of human memory, how do you think it would correspond to something in the real human, let's say, brain?
Yeah.
You understand what I mean? Or, no, not so much.
Yeah.
So there is no more question. Thanks you again.